It gives me great pleasure to introduce my almost neighbor, Professor Kyriaki Kalaitzidou. He is the Ray S. and Frank H. Neely Professor, and also our Associate Chair for Faculty Development here in the Material Science Department. Frank Neely, if you don't recognize that name, was the name on the Georgia Tech nuclear reactor that was built pretty much right here where this building is now, so a little crossover there. And I'm definitely picking your son for basketball next year now that
Thank you.
Her son and my son occasionally are the same age in terms of that, so he's very good at basketball. So
Thank
I
you.
want to team.
I want to believe he takes after me. I just want to also say that I'm in mechanical engineering. Make sure that my boss doesn't complain. Yes. So I will talk about towards cradle-to-cradle circular economy. Where are we now? And I would like to ask you to bear with me because I will start with some basics to make sure that we are all on the same page. And then I will zoom in my work is in manufacturing of polymer composites, polymeric materials and polymer composites. And so I will give specific examples on circularity and cradle-to-cradle philosophy when it comes to polymers and polymeric composites. So what is our current philosophy? Our current philosophy, manufacturing philosophy, is cradle-to-grave. And that really means we use it, we lose it, which means at the end of life, and then we just bury it in the ground. I became aware recently that we also send it in with satellites to go around the Earth. Maybe later we'll send it in the moon. And it doesn't stay in the ground, of course. It goes to water, to the seas, to everywhere. It goes to the air because it's particles that pollute the air and so on. And so what is the cradle-to-cradle I'm talking about? So in the cradle-to-cradle philosophy, every piece of a product can retain value at the end of its current use cycle and makes a positive impact forever. Ideally, it's a circle and you don't get out of the circle. Examples of cradle-to-cradle approach are buildings with roofs that can be used for farming, carpets that filter particles from the air, wall plaster that absorbs airborne toxins. So it is not just you reuse it, but you actually get an impact, a positive impact out of it. So nature knows best, right? So the circular economy is nothing new that we invented, and it's a cool buzzword. It happens in nature forever, and that's the cycle right there. So from soil nutrition, plants and trees are growing, animals are fed on plants and trees, and when at the end of life of animals, they are converted to decomposed and feeding into nutrition, and the circle goes on. So this is exactly what we need to do and mimic nature. And this is how the cradle-to-cradle manufacturing of a product would look like. We can think of the manufacturing using renewable materials. And then we get the product, we do the consumer buys the product, we use it, and then we disassemble it and recycle it back. And you see there is no input or output in this cycle. It should be self-sustained. So this is the ideal cradle-to-cradle. So this is not just a philosophy. Apparently, there is the Cradle-to-Cradle Product Innovation Institute. It was founded 2010 by William McDonough, Michael Brunelkart, and Bridget Cluttergord. The first to actually started with a book, Cradle-to-Cradle, and then based on their work, they formed this institute. And what the institute does is the institute actually trains consulting firms who help companies to go through Cradle-to-Cradle certification program. And when they are done, they send a report to the institute, and the institute will approve if they pass or not, and they get the certification. So what does that mean? So the certification requirements, products are designed for end-of-use disassembly and recovery. All of these requirements need to be met in order for the product, for the company to be certified. Use of renewable energies, maintaining and enhancing water quality, honoring social fairness and human dignity, continuous and aspirational improvement, and materials might be safe to use and reuse. So that's it. We have the institute, we have the certification process. Are we done? Are we there? Not really. So right now, there are 13 officially accredited assessors, meaning consulting firms that can work with industries, companies across the globe. There are 200 plus companies that have been certified, 360 certifications that have been given out, and 2,800 products in total. So understanding, just looking the world around us, we are way more than this number of products and processes and companies. And so we still have a long way to go. So this is the big overview of what cradle to cradle means and where we are overall. And then I want to zoom in a little bit when it comes to polymers and composites. And so if we think of this thematic representation of the circular economy of a product, of material, right? And I want us to start from where it says the arrow that goes in the responsible extraction. I labeled as 1 and go clockwise, right? When it comes to polymer sourcing and material manufacturing, currently both the energy that is used to make the polymers and the feedstock for the polymers is based on fossil fuels. The majority of it, petrochemical industry is still flourishing to this day. And there are major efforts. And so we are making polymers using monomers that we find in nature. Polylactic acid is an example that is made out of cornstarch through enzymatic processes. We can use some other monomers in nature. There are microorganisms that actually make polymers. But all these polymers are not there yet in terms of performance and definitely in terms of cost. So industry is not easily going to adapt them. They don't meet the requirements, and there are no really incentives, to be honest. So there is some effort, though. When it comes to manufacturing then, right? So you make the polymer, you need to make composites. What do you need? You need more energy input, you need resources like water, you need, you have a lot of like polymers, you have fibers, and there's a lot of waste streams. You pollute the water, there's a lot of waste streams that go in landfills, and the energy, the majority of the energy that is used in the manufacturing of composites in these industries is not really renewable at this point. Then if we look at this distribution, so the composites, these parts are made, these final products are made, and then there's so much room in the distribution section, because from the trucks that drive these products around, are they using renewable energy, to the packaging that is used for one single use. And so there is so much to be done with either policy, with marketing, with a lot of room. Why to use single wrapped products? We can get family packages, right? There are many, many different ways, and it's really about marketing. And also, then if we move to the use, right, again, marketing and policy has a lot to do with it. There can be different business models that we do things. Instead, we can lease a car versus buy 3 different cars per family, depending on our needs, right? There are different models when it comes to how we are using the products. And there, of course, there is a lot of educating the customer, the consumer, that it's not there yet. And then when it comes to resource efficiency, repair, and we have a major effort in Georgia Tech through the GTMI, the Georgia Tech Manufacturing Institute. Ben Wang and Chang Zhang have a big project, a big program on repair of composites, because you extend their life, and then reuse. But if you come to think about it, it's a problem of distribution, because when I generate waste, the system is not there for everything to be collected and taken back to a central location, right? I'm eating my candy bar. This is a very small volume, but it's many of them distributed all over. It's very difficult to collect them. It's very difficult to make a case that there is value in this. And if we talk about just repair and reuse, and if we focus only in one of these, then the only thing that we are doing is that we are just extending the time before it goes to landfill, right? Or just expanding a little bit the life, the service life of the product, but we are not doing anything else. So if it doesn't go in X time, it will go in X+1 time, but really it will go to the landfill. So we cannot just look at one of these aspects, one of these 7 steps. We need to have an overall, an integration, and an integrated approach. And then if we think about the collection, I already mentioned the scoring and the manufacturing, right? We know in polymers that when polymers go back to be recycled, only thermoplastics at this point, they are thermally degraded every time they are reprocessed. So eventually, we don't really recycle them, we downcycle them. And the key is not really to just recycle them. The key is to take them and break them to their monomers or other useful chemicals. And there is a lot of effort also in Georgia Tech on that. The example I will give is the work led by Professor Karsten Sievers in chemical engineering, who does mechanocatalysis of polymers and breaks them down to monomers. And there is a lot of effort also through the RBI, through the Renewable Byproducts Institute. And then it goes to landfill. So ideally, whatever goes out to landfill should be 0 for cradle to cradle, but realistically speaking, it should be very small. And then whatever comes in, it should be also minimum and recycled. So these cycles should be self-sustained. So if we focus a little bit more now on composites, and I will talk about carbon fiber composites, glass fiber composites, and then a couple of other examples. So first of all, a background for carbon fibers. The way they're currently made is not sustainable. Why? Because they are very, very energy intensive. And so the energy that it's not from renewable resources, and the precursor material, the precursor fibers, which is the feedstock to make the carbon fibers, is polyacrylonitrile, which is a polymer which comes from fossil fuel. So it is cost prohibitive for white applications. It is energy intensive. However, despite that, there is so much need for carbon fiber composites applications. If the cost was only lower, carbon fiber composites would have been used all over the place. So they are very high, sorry, I don't know why it's messed up there. They're very high performance, high cost, single use materials. It's only like when they first start they used like maybe in the 80s, early 80s in commercial airplanes, right? So this is the time now that these planes are decommissioned, and we start seeing the carbon fiber composites in landfills. And we will see way more of this. So very high cost, very high performance, very high demand, energy intensive. The projected global market in 2018 was $4.7 billion in 2019, and it will be $13.3 billion in 2029, just for the carbon fibers themselves. Now, I want to give you some perspective. Okay, carbon fibers. What about the carbon fiber composites? So the market projection for that is $23.24 billion to $33 by 2025. And as I said, it's cost prohibitive to use carbon fiber composites in automotive industry. But if we were able to, if the cost goes down and we are able to, then if we make the car body from carbon fiber composite, it will be 75% lighter than now that it's made out of steel, which means the fuel efficiency will go up. There is a 10% reduction in vehicle mass, yields 7% increase in fuel efficiency. So you can do the math and you can think about the number of cars available and how much carbon fiber can enable in terms of saving gas, right? However, as I said, it's cost prohibitive. So let's assume, let's look more what happens at the end of life for fiber composites, right? And these are presented, these end-of-life strategies are presented in an order from the most impactful, most greener to the least. So we can do lifetime extension, return to us same as new or upgraded condition and performance. And we can do pyrolysis. It's a process to recover fiber char and gases for energy. We can do a kiln, a cement kiln, and you need to heat it up 1,000 degrees. It's a lot of energy intensive, and you recover gases for energy. You can regrind and reuse, but now you start losing the properties of the fibers because fibers are contributing because of their high aspect ratio and so on. And it's mainly a mechanical processing into pellets and using it then to make new products. And you can just dispose them to landfill. You get nothing out of it. And you're just turning earth into a graveyard. And so here is now I'm comparing. This is work by our colleague in MSc, Satish Kumar. And so in the first column, you can see the characteristics that I will be comparing. The second column is the current approach, the current technology. And the third column is the proposed approach. So the energy input, as I said, is very high. You need to heat them up. There are multiple stages during the manufacturing of the carbon fibers. What Satish does is that he proposes, first of all, to use less energy, almost 80% less energy. And the way he achieves that is by Joule heating. So he is making the precursor electrically conductive, so he doesn't need to heat the fibers at different stages, the precursor as much. So that's one innovation. The cost will go down because now the energy input will be lower. The applications, because the cost go down, currently aerospace and high performance applications are only allowed, but carbon fibers can be used everywhere if the cost goes down. And then the carbon footprint during the service life, of course, it's low now, and it will be even lower because more applications will be enabled. Also, I didn't talk about the feedstock. The feedstock currently is 100% pan fibers, polyacrylonitrile, or pitch, still coming from fossil fuels. Whereas in Satish's case, he's using 50% lignin. So up to 50% reduction in the fossil fuel dependence when you make carbon fibers. And the end-of-life strategies are mainly currently landfill. And in this case, and this is how we work together with Satish, is we can actually reclaim the carbon fibers because carbon fibers have a sizing, a coating that will allow interactions with a polymer in polymer composite. And so we are using materials for coating is sacrificial. We can dissolve it away and it will be easier to reclaim the fiber with minimum damage to the fiber. So then that's about carbon fibers. And you are probably aware also about glass fiber composites, right? And so glass fibers composites have been used for quite a few years, but recently they're used mainly in harvesting wind energy, right? The blades in the wind turbines. So the projection is that by 2050, there will be 200 to 400,000 metric tons of end-of-life glass fiber composites. And here I will present a very brief, big picture of a project from a colleague here, Professor Russell Gentry from Civil Engineering and Design. And the project or the consortium is called Rewind. You can see the members of the consortium, the different projects, some funding. And really, this is one of the aspects of the cycle that I show you, that they are going to reuse, to actually repurpose with the wind blades with a minimum amount of energy input. And so the first one, blade bridge. So this is a concept to convert an entire wind blade or a large portion of it to main load bearing elements for a pedestrian bridge. And it is working with the University of College Park and Munster Technological University as primary partners. And you can actually see the real bridge that is made, and it has been installed in Cork, Ireland, earlier this year. And what Professor Gentry does is that they are doing the mechanical analysis, because these blades are at the end of life, so of their service life, right, as blades. And so they want to see what is the fatigue, how much load they can take, and different types of loads, and do all of that. And then they feed that into civil engineers who will actually build the bridge. And there are a couple of bridges, but I think in progress, but this one has been installed. And a second approach, actually there is a catalog of all these repurposed applications. The second one is blade pole. Again, they take the blades and they will replace the wood poles or the metallic poles for the electricity. And this is full-scale testing of braced line post assemblies for gravity and wind loads. And these will be standing out, and so they need to test them for all different conditions. Again, this is at the end of life, and so these materials have already gone through a lot of loading and different conditions. And here is actually, so the first phase was actually doing the mechanical testing and everything. And then the second phase, they did installation at Smoky Hills, Kansas, of in this arrangement of 4 blade poles, the way you see it, and it's out there. And then 2 more other applications that they are already out there. Again, this is the bare minimum amount of energy that they are putting into end-of-life project to make something useful out of it, and to make something where the materials used before in these applications were virgin materials, right? And so noise barrier, 6 meter high. You can see the details here, vertical full sections. These type of blades have been used, and they can be, depending on the statics they do on the acoustics, they can use them in regular or irregular arrangements. And then feed banks. Feed banks or water banks for animal farms. These materials, in this case, the application is not structural, and it doesn't take a lot of load, but it can take all the environmental conditions, and it can be easily transferred. And the other thing that it's mentioned here is that all these applications can actually take place next to the windmill. So you don't have transportation, you don't need to think of anything. And if you go now to a windmill, that you can see how ugly it is, because every broken blade is actually on the ground. So I covered carbon fiber composites, glass fiber composites, and now I will give you an example of multi-layer single-use packaging, which is mainly, it's not a composite, but it's multi-layers, different layers of polymers. And so as you see in the schematic here, you can see nothing is circular about it. It's quite linear, right? We use fossil fuel energy. We make these different types of materials and layers. We laminate them together and we use them as packaging for many different products. At the end of life, it's very difficult to retrieve all the different layers. There is a lot of major effort done, but we're not very successful. And these materials will find their way into the landfill or the sea, right? And so just to give you an idea of the magnitude of the problem, just in 2015, the global polypropylene and polyethylene packaging waste was 82.7 metric tons. And based on this waste, the debris, the plastic marine debris, it affects 267 species globally. The majority of them, 86% of the sea turtles, are affected by this, and more than 40% of seabirds and marine mammals. But it's not just that, if that is not enough. There is a lot of cost associated with this, because plastic aquatic debris has direct financial consequences. For example, in communities like California, Oregon, and Washington, where 85% of the population lives along the coast or waterfronts, there is a major cost, $520 million a year, based on an EPA report, to actually combat litter, prevent trash from becoming marine debris, and so that these areas do not lose the recreational value, right? So something needs to be done. And so what we propose to do is that, and this is something myself and my colleagues from material science, Professor Jacob and Stigilin, and a colleague from environmental engineering, Konstantinidis, are working on, is that we take this multi-layer packaging and we will be using an adhesive that it is sacrificial, which means that at the end of life, whenever we want, we can trigger this and we can remove it. And so then the idea is that these layers will just float free and they can be collected and recycled, right? And so that's the whole idea here. And these layers then maybe can also be biotransformed. So instead of just recycle and take the polypropylene and melt it again, we will identify bacteria that will take the polypropylene and make it to gas, to methane, to something else. So we are talking about biotransformation. And then another example that we don't think of often very much is carpet industry. And here is the issue. Carpet industry is like, carpets are literally multi-layer, like multi-layer packaging. They have the nylon fibers, and the nylon fibers are totally recyclable. You know how to do it. But really, they have a couple of backing films where the nylon fibers are bonded and come together, that these are adhesives. And because of that, we cannot recycle the nylon fibers, and all of the carpets are very difficult to be recycled. So there are two ways to go about it. Either you replace the thermoset adhesive with a thermoplastic, so you can recycle it, but thermoplastics are not very good they don't have very good adhesive properties, and then the quality or the service life of the carpet or the quality of the carpet is not as good. Or again, you can use a reversible and a sacrificial adhesive, and at the end of life, you can just dissolve the adhesive away. And so again, this is about 108 billion, the carpet industry, and the bottleneck in recycling, reusing is the adhesive. And so, so I talked about the adhesive, and I told you that's what I work on, and so I thought I better give you some proof that indeed I'm working on it. And so here is some chemistry, but I'll keep it really big picture. Believe me, it will not be hard to follow. So the idea is to create these epoxy networks. Epoxies are very good for adhesives, but and then to have bonds that can break a bond demand. That's all what we are doing. And so we are starting with the monomers, and the epoxy is in the middle, as you see. I actually have a laser pointer, I figure out at the end. So we have the epoxy, and this is the common epoxide group in all adhesives. And then we bring in some of these end groups. And so both of these come from renewable resources. So depending on how much I will put from this and this, I can have up to 30% epoxy made out of renewables. But that's not the key here. So that's one aspect. The other one is that they react and I make my prepolymer. Then I take the prepolymer and I use this as cross-linker. So many of these will be connected to each other using these as bridges. Either that or that, I can use different chemistries. The reason why you use different chemistries is because we really want to mimic the behavior, the mechanical behavior of the normal epoxies, of the regular epoxies. And so we try to understand how we can get closer to that. But when these bonds, so you can see these bridges, right? These waves are my prepolymer, and these blue and red bonds are these. So these bonds can break upon heating. And once they break, I go from a very rigid material to a soft gel-like material. And because it's a soft gel-like, I can wash it away. I can remove it with a solvent. I can even fine-tune it, and the solvent is water, if this would be a water-borne epoxy or something. And so the idea is that I break this and I retrieve this, or I take it away from there, and that was keeping together all the different layers, and now the different layers are able to disconnect and be reclaimed. And here is a little proof. So these are 5 cycles of heating and cooling my material to show you that you see the same thing is happening in every cycle. This is the energy that it's coming out of the reaction. And so you see all 5 blue are the cooling cycles. All of them are on top of each other. And the red ones on top of each other, only the TG has shifted in the first cycle. So this means that the energy that goes into the system, that comes out of the system for the reaction is the same in every cycle, which means I'm able to do the same reaction back and forth. This is for 5 times. And here is like this, the scratch is like I broke my bond, right? And then I'm heating it at different times, different temperatures than when I broke the bond. And you can see that it self-heals. And so I can repair it. I can still reform it. So with that, I would like to answer the question I imposed in the very beginning. Where are we in the cradle-to-cradle economy? We are not there yet. I think it's not difficult to figure that out. Just to remind you, what we want to do is that we really want to have this circle going forever with minimum input and output, right? And as I said before, it is not about working. Each of us is doing something little in one of these 7 colored zones. But it's really what is needed is major collaborations across different disciplines, from chemistry and physics to make new materials, to industrial engineers on the logistics, how to distribute them, to designs, to manufacturer, to mechanics. And then partnerships between academic and national labs and industry are really needed, because in academia, we don't have the scales, we don't have the quantities, we don't know if everything we do in a small scale translates. And sometimes we may not have the resources. New policies and regulations and new incentives. We don't have incentives, and the marketing is not great, right? We can have one of these very like famous people that are very popular advertising something, and then everybody will go after it. So why don't we just use our pop culture and market better when everybody sees the value of this, but I don't think we go after it. So with that, I don't have an acknowledgement slide. I think I acknowledge the people as I was going through. With that, I would like to thank you for your attention and for the invitation, and I will welcome any questions.